clarify a couple of things that might be really helpful to you. If you have acquaintances who show up and you like them enough to pass this information along, it wouldn't be the worst thing you've ever done in the world. There are a couple of things that I want to make sure that everybody is aware of. I've had just a couple of emails about assignments, and essentially what I have laid out is that as long as you are using your class time, there's always going to be opportunities to bring up scores. I'm not looking to use the points on an assignment to be punitive. But if you look at a score and you don't like what you see, whether it's because you got a B and you want an A, or whether it's because you got 50% and you want at least a pass, then there's a couple of things you can do. One is you're always welcome to talk to me or email me, and I'll let you know. The other thing is that typically there's going to be some, if you missed a bunch of points, there's going to be something glaringly obvious to you if you look at the assignment that you didn't do. And so for the conservation of mechanical energy assignment, there were a bunch of you that didn't get full credit for any one of a number of reasons. So I just want to go through that real quick, and I'm not gonna solve all the problems for you. I'm just going to point out a couple of the things that you might think about doing. And the first is that there were three big parts to this, I guess four if you consider the part that I did. The first part was to make a prediction using this equation about how high up a cart would go, not how high above the ground, but how far along a track a cart would go if it's launched from its built-in spring. And if you go back through, maybe you missed this at the time, but if you were here, you probably remember, and if you don't remember, you can go back through the notes online. I derived the equations for you, and there were two of them. One allowed you to predict the change in height of the cart, and the other allowed you to use an angle, which you'd have to either pick yourself, or you could use the one that I said. I think I said 7 degrees, but it doesn't matter what the angle is. You would use that to figure out how far along the ramp the cart went. Right? So I derived the equations for you, but I wanted to see that. And then the second piece was to find K of the spring. So one of our equations in here, it involves K. So if you launch it from a spring that's fully compressed, then that means that all of the energy is elastic potential energy. That means that in order to find a number there, you have to have K. And I showed you how to find K by taking measurements and making a line of best fit. And I wanted to see that in your lab, right? So that was the second thing. And then using that information, I wanted you to make a prediction. And the prediction should have been what I was calling D. The variable doesn't matter. You could have called it M, or like mu, or anything. It doesn't matter. But what I was speaking about was this right here. This is what we wanted to predict. So you've got your cart here. You've got your ramp like this. There's some angle that you either determine or you know. The cart itself can be measured. There's information about the spring that you need to know in order to be able to determine the initial energy, and you can use that to find change in height, and then you can use that to find how far up the ramp it would go. So that's the prediction that I was looking for you to make. And then I wanted you to test your prediction. And ideally, you would have made several tests, and ideally, you would have evaluated it in some sort of thoughtful, physics-based way why it was that whatever it was that you predicted, you never got. I mean, if anybody here got to within 1 centimeter of their predicted distance, it's only because you made some other mistake, right? Because there's no way that all of the energy from the spring really ended up being transferred to gravitational potential energy. It didn't happen. So you would have seen differences, and there are some explanations for that difference. One is right here, which is that no matter how well you set up this experiment, your prediction is always going to be greater than the actual distance. If you would do everything right, then you should have overestimated how far your car went, because some of that energy gets lost, even in an absolutely, like, the best designed system with the best equipment and, you know, no lateral motion and everything is just like, it is like, you know, a $400,000 cart set up with titanium springs and all of that. You're still gonna be off, maybe just by a few millimeters, but it's never gonna match, and that's because of this. Then there's a whole bunch of other things as well that you might have thought about. In general, what I've been trying to have you think about is the idea that we have these built-in things that we say that are really meaningless if you think about it. Things like measurement error. If you just say measurement error, then what you're telling me is something went wrong. What? You don't know. Or calculation error. What does that mean? It means that you didn't really think about what might have gone wrong. It means that you just know there's always a few things. Measurement error, calculations, equipment error, human error. Like, those are always the case. What we want to think about here is, what would you do differently if it were your job and you were going to get paid a bunch of money to make it work better, right? So if, for example, you get within 30% of your target distance, it's not terrible, but you could do better. How are you going to do better? Equipment error. No, it's not. What is the error? What is the problem with the materials that we're using? And how could you potentially fix it? I'll give you an example. These carts work by having the spring lock in like this and then push out on something. But if you have the cart, oh geez, sorry. If you have the cart up against the back of the ramp and then it does this, it rolls away just a little bit, then we're not gonna get all that energy transferred, right? Like, that didn't go nearly as fast, and it's not gonna go nearly as far as it would have if the cart were actually pushed as close to this little block as you can get it. So one thing that you could do to improve the transfer of energy from the spring to the cart is make sure that that plunger is touching something before you hit go. If it's even this far away, then you lose that much energy because that spring isn't pushing on anything. When that happens, it just doesn't really accelerate the cart. There are other things you could do. You could triple check the angle of the ramp with a really good inclinometer. And it may be that your phones are all calibrated the same, but it may be that one of you has a 2012 Galaxy S3 and it's cruddy, and somebody else has an iPhone 19 Pro Titanium Super Max, and that will calculate within a 1/1000th of a degree the accurate angle with respect to the Earth's gravitational field, so maybe you use that instead. The tracks themselves aren't perfectly straight, so one thing you could do is support it in a couple of spots to make sure that it's level along the whole. There's all sorts of things that you could specify. I wasn't looking at the error analysis of this real critically. So that's not something that's gonna give you a whole bunch of points, but it actually is something that's really cool to think about, is the difference between if somebody says, what happened here, and you're like, I don't know, equipment error, measurement error, human error, calculation error, I don't know. and a determination to make it better. And I'll just a tiny little segue. I've been listening to an audiobook by a physicist who is kind of going through the history of modern physics. And one of the things that she's talking about is how in the late 1800s and the early 1900s, these scientists were just, like, everything was trial and error, and everything was made by hand. They were making, in the lab, their own vacuum tubes, and they were like hand wiring electric. You couldn't just go to the store and buy something, you had to make it. And it took them years just to make something that we could now go to the store and buy in a second. And that, of course, is ridiculous overkill for 99.999% of the people that are going to go through this school. I hate computers. And, some of you might actually go into engineering where that kind of attention to detail is going to be important. And more interestingly, it's just kind of fun to think about. So even in the context of this classroom, like, you do something, you make a test, you try something, and then, gosh, see if you can make it better. And my experience personally is that's really fun. It's really kind of rewarding when you're like, okay, what can I do differently? Even, like, I put it away now, but I have a little spray can of WD-40, because one of the things I was thinking is, like, if you are, like, noticing that your spring is catching, then you're losing a ton of energy. It's not accelerating the cart, it's like pushing on metal stuff in there. So I don't know, I thought maybe you put a little WD-40 on the spring and maybe you get more closer to your prediction. Those sorts of things can be fun. All right, and then, so all that stuff needed to be there, and then there was this big piece here, the energy story. The energy story, I gave you an example, it's posted to Canvas if you weren't here or you forgot, but what I essentially wanted you to do is tell me, in this activity, where was the energy at the beginning, where was it when you made your final measurement, and how did it get there? Which forces were doing the work, what were they pushing on, and how were those things moving as a result of those forces being exerted? And that energy story, so there were a couple of people, I don't remember if it was this class or the other class, who told the energy story of something else. They like described something falling, but this isn't falling, this is motionless and then accelerating at a diagonal up a ramp. I want that energy story. How did the energy get from the spring to the gravity spring? How did that happen? What were the forces that were involved? What were they pushing on? How are they moving that caused that energy to be transferred? That's work. Work is force exerted on an object as it moves in the direction of the force. So if you did not get all the points that you want on that, almost certainly it boils down to one of these things, including the energy story. And in general, so if you go back and you look at other assignments, if you see you got like a 2.5 out of 3 or you got a 2 out of 3, is because you forgot something. You just didn't, there was just some part of whatever it was that we were doing that you did not get. So if you can figure it out by looking at the assignment, right on. If you can't, come and talk to me and I'll clarify for you what I was looking for. All right, so that's the conservation of mechanical energy. And then the other thing that I'd like to do is go back to, we're gonna continue working on the pendulum, predicting the motion of the pendulum. And I just wanna remind you all that what we had decided, and we didn't quite wrap this up, but I'm gonna just short circuit, because I think everybody got here. I was like kind of winding my way there, but I think everybody ended up figuring out that this is really the only thing that you can change about a pendulum that makes any difference. And what you, sorry, let me be more clear. This is the only thing that matters to determine the period of a pendulum. You can change the maximum height by changing its starting position. That will also change its maximum speed as it passes through the equilibrium point. But the period the pendulum stays the same. The amount of time it takes to make one full cycle is always the same. Any pendulum that we build, and the only thing that matters is how long the string is. Now, there are a couple things that we could do to throw a monkey wrench into this. One is we could have a really poorly built pendulum, so that will mess it up. Another thing that we can do, and we'll talk about this tomorrow, it turns out that pendulums don't really exhibit simple harmonic motion. They just come so ridiculously close within an angle, a cone of about like 30 to 60 degrees that basically it works. But the higher up you lift that ball, the less it's simple harmonic motion. Everything breaks if you lift it up past about 30 degrees to the horizontal or to the vertical. But at this angle or less, you will have something that is effectively simple harmonic motion. We'll talk a little bit more about it tomorrow because it's kind of a cool idea. So what does that mean? That means that if you were to change the mass, if you were to change like the speed at which you let it go, the height at which you drop it, the period is basically going to stay the same. The only thing that changes the period of the pendulum is how long the string is. So there was another part to this activity, and this is what I want you to do today. I want you to look at I want you to actually collect data. So I want you to measure the length of your pendulum and measure the amount of time it takes to make one full cycle. And you can replicate this. So if you want to do like a 4 centimeter pendulum and measure the time in seconds, then you should get roughly the same time for a 4 centimeter, and then roughly the same time for a 6 centimeter, and then a 10 centimeter, whatever it is you decide to do. But I'd like you to collect some data and then make a graph. And the graph should be a graph of L, the length of the string, on the x-axis, and time, the period of the pendulum, on the y-axis, to see if you can not only say, like we already figured out, this is what matters, but beyond that, what is the mathematical relationship between them? You're not going to come up with an equation, because it depends on some other stuff too, but what you will come up with is a type of relationship. It's going to be linear, or quadratic, or inverse, or something, and we can categorize the relationship by looking at the shape of the curve, and that's what I'd like you to focus on. And then I'll work with you, and Ms. Adams will work with you, but once you've got that and you feel reasonably confident about where you are and what you've come up with, then we'll get that turned in, and then tomorrow I'm going to fill in some of the details, but you should all see the same general shape of the curve. It's going to be pretty obvious, and many of you are going to remember the name for that type of mathematical relationship. Okay, so before we spring into action, does anyone have any other questions? There's no springs here, though. There were. We were springing into action. Now we're swinging into action. Do you think anybody's ever been fired for making a dad joke like that? Do you think I could lose my job for telling you all to swing into action on a pendulum project? Okay, let's see what you can do.